Good. So thank you for the introduction. So after the layout and design by Katarzyna, I'm going to speak about the fabrication of the silicon photonics. So first, a few words about CEA Leti. So we are a research institute in Grenoble with very large facilities for the clean room fabrication for format wafers of 200 and 300 millimeters. And I'm part of the Optics and Photonics division, which is part of the CEA Leti, and it's 300 researchers, and we also have a dedicated clean room for photonics application. So then I'm part of the Silicon Photonics Lab inside this division, and we have several subjects, several applications, domains that we target. Starting from the right, quantum photonics, but also neuromorphic circuits. We have a lot of work going on LiDARs as well. And the subject of today is, let's say, the historical application of silicon photonics, the high-speed interconnects, optical communication. And you can see here a schematic of a circuit. Maybe it's a bit small, but you have the main elements of a transceiver with a laser source, a modulator with a driver, with several channels in parallel, a multiplexer or demultiplexer, and a way to couple out the light to the fiber. So the outline of this presentation. So first I will speak about the silicon photonics platform and give you some information about the fabrication and the device libraries that we have developed for this silicon photonics platform. And then I will focus on a few building blocks that are useful for the platform. So first, a process building block to lower the losses in silicon waveguides. Then the integration of another material, silicon nitride, to do 3D photonics, which is very useful and that we use in the MASSTART project. And then two other interesting features. First, a way to test edge coupling at the wafer level. And another platform that can be very interesting for data communication as well, which is high-quality silicon nitride. So first, the silicon photonics platform. So we have developed a silicon platform for 300 millimeter wafers. So you see the cross section here with first SOI level. So we can start with 300 nanometer thick or 220 nanometer thick SOI. We use immersion lithography to pattern the silicon with a feature size down to 60 nanometers. So to realize this this cross section, it's a very long process. We have more than 200 steps and 24 levels of lithography, and there are several process building blocks to achieve this this cross section. So several levels of patterning for silicon, dopings for PN junctions, germanium for photodiode, silicon nitride if it's needed, and then a two-level backend of line. So in parallel to this fabrication platform, we have developed a device library with passive components. First, routing elements, waveguides, splitters, directional couplers, MMIs, coupling components, so 1D or 2D grating couplers, but also some multiplexers, some ring resonators. So this platform with a library is available in MPW runs and that goes with a PDK. Then we have developed also active components. So the main active components are first the photodiode based on germanium epitaxy. So you can see here a picture, a top view of the germanium photodiode within a silicon waveguide. Here it's a cross section with this specification for the germanium photodiode. For the modulator, we use classically Mach-Zehnders modulator with PN junction. So here you have the cross section. Here you have a top view of MASSTART circuit with 4 Mach-Zehnders modulators in parallel. An example of a modulation at 64 gigabit per second NRZ. And typically we have an efficiency VPi LPi of 1.5 volt centimeter and losses for the doped waveguide of 7 dB per centimeter. A very important building block, but separated from the other, is a hybrid laser. So 3.5 on silicon hybrid laser. So it's a more complex process, but we have worked on this subject too. And it's not part of MASSTART, and it's not accessible, available in MPW, so I won't speak more about this subject today. But if you have some question, you can ask me afterwards. Okay, so now the specific building blocks. So the first one, I'd like to have a focus on the silicon waveguide. So it's very basic, but it's important, I think, because we have developed a process to do smoothing of the waveguide in order to reduce the roughness of the waveguide, and it's very impressive in terms of loss reduction, propagation loss reduction. So we can achieve propagation losses below 1 dB per centimeter, depending on the wavelength, for strip single mode waveguide. And if you have a look at the improvement in terms of without annealing in blue here and with this annealing process in orange, the improvement is very impressive. And we have so very low propagation losses for silicon waveguide. So it's very interesting when you have a complex circuit, like in a transceiver circuit with a lot of elements and long lines, so you can gain several dBs. A question is there an impact on other devices? And the answer is almost no. There is no impact on grating couplers, for example. And here I plotted the efficiency of the Mach-Zehnder modulator, Vπ-Lπ, and in this direction, the insertion loss of the Mach-Zehnder modulators. And you can see that we can reduce the insertion loss by several dBs without changing the efficiency. So it means we doesn't change anything about the PN junction during this process. So it's very interesting for this type of application. Another add-on or building block which is very important for Datacom is silicon nitride. So in the MASSTART project, we use silicon nitride for two reasons. The first is for multiplexers. So the multiplexer AWG is in silicon nitride, and we can take advantage of the low thermoptic coefficient, which means that the multiplexer will be has a low sensitivity to temperature. The other reason is the coupling to the fiber, and using silicon nitride with a lower effective index, we can have a better mode matching using edge coupling. So here you have a picture of a MASSTART circuit with the Mach-Zehnder modulators and NWG silicon nitride multiplexer, and some characterization results of this multiplexer and the edge coupling. Okay. So now I'd like to say a few words about edge coupling. So from our point of view, when we fabricate wafer, we like to test our wafer quickly with an automatic probe station. So we don't like edge coupling because it's difficult to test. We have to dice the wafer, we have to align chip by chip, so it's not very convenient for us. And so we have demonstrated a solution to test the edge coupler devices or the edge coupler itself at the wafer level. So the schematic is here, and we use a WAFT, waveguide array to fiber transposer, which is fabricated by Teams Photonics. When we have glass waveguides with a mode which is matched to the mode at the output of the silicon nitride waveguide. And we can have this WAFT in front of the waveguide in the PIC, in the photonic integrated circuit, thanks to a cavity etch that we etched anyway, because when we dice the chip, we etch in the middle of the cavity, then for the packaging. So with this solution, we can test devices with edge coupling scheme very easily on a prober. So it's very interesting, I think, to show that. I don't know if I have time. Yeah, maybe. So the last feature, so it's a bit different from what I presented before. It's another platform, but I think it can be interesting for Datacom and for high data rate transceiver. So it's the silicon nitride, but silicon nitride only and based on LPCVD. So it means high quality silicon nitride with very low losses. So using this type of silicon nitride, we can have losses around a few dB per meter. So it's 1 or 2 orders of magnitude below what is done in PCVD, for example. And it means we can achieve quality factor, ring resonators with quality factor of several millions with high confinement. And it gives the opportunity to generate frequency comb. And we have demonstrated frequency comb. Here you can see this picture with a ring resonator. And this has a potential for parallel optical communication with a lot of parallel channels. And so to achieve very high data rate. So there is, for example, this example by the Kippenberg group, where they show 50 terabit per second with this type of device. So I think it can be very interesting for optical communication as well. Okay, so this is the conclusion. So I spoke about the silicon photonics platform that we have developed in Leti, which is associated with a PDK and a device library, passive and active components, and which is open to MPW runs. And I had some highlights about the integration of silicon nitride on top of silicon and the test of edge couplers at the wafer level. And this nice LPCVD platform for silicon nitride for frequency comb generation. So thank you for your attention. Thank you to my colleagues at Leti and within the MASSTART project who helped having these results. If you have some question.
Thank you, Quentin. There's one question on the chat on the slide number 6, the size of the length grating couplers and the tapered waveguides.
I don't have the slide number. Is this one?
Number 6, I think.
Okay.
You can go back.
Yes, this one.
2 more. Yeah, there. So the size of the grating couplers and the tapers.
Okay, so the grating couplers, it's designed to match the SMF28 fiber. So the optical mode at the output of the grating of the 1D grating coupler or even the 2D grating couplers, it's about 10 microns for the mode field diameters. In terms of dimension, the taper, I think it's around 30 microns for this taper here. If it was a question.
Yep. Thank you. I hope that answers the question. Are there any other questions? We still have time for one more question. If not, I will. Okay. There's another question. Coupling losses between the WAP and the silicon waveguide.
Okay, so we had some preliminary tests. So if we couple a waft and a chip, not this scheme, but a diced chip of silicon nitride taper and a waft, the smallest loss we saw was 0.8 dB. And here, in this case, the alignment was not so easy, and so you have on the right the losses a function of the wavelengths, and it's around minus 10 dB. So it's a high loss, but the point of this scheme is to test circuit with edge coupling. So we don't mind if there is 10 dB at the input. It's just to test that the circuit is working. So it's not a problem for us.
Thank you, Quentin.